Thank you very much for the invitation. It's a pleasure to be here. And I'm also very happy to see that we have a panel on optimization or control in this conference. This is an area in which we have amazing Turkish representation, especially Turkish women representation. So I'm very glad that this area is represented in this conference as well. So what I'll do is I'll talk about general broad area, emerging area of large-scale data processing and large-scale networks, decisions and optimization for large-scale data processing and networks. I'll basically try to give you the challenges in this area from a very biased perspective, of course, from my perspective, and also give a couple of examples from our recent work to highlight the type of problems, questions that our research community is interested in this area. So just quickly motivate, and Tamer Hocam talked and set the stage very nicely. Decisions and optimization in systems arise in a wide range of applications. So for electrical engineers, a prominent example is clearly data networks or computer networks. And by this, I'm thinking about computers connected to each other, which allows them to exchange data. This is a huge network in which we have computers communicating with each other. This supports applications such as email, file transfer, voice, audio, video. So, of course, the Internet is the best-known example. And there are fundamental resource allocation questions here in terms of thinking about you have data packets. How should I send this data packet from origin to destination computer? Which routes should I pick? How should I schedule this? So this is a clear optimization problem. In signal and image processing, we have zillions of problems, filter array design. A contemporary one is compressed sensing, where we're trying to both acquire and reconstruct sparse signals using far fewer measurements than typically obtained. We have problems, optimization problems in communication, transmitter-receiver design for MIMO channels, power control, and also in business applications, ranging from manufacturing, supply chain design and management, revenue management, pricing, as well as financial engineering. And I tried to sort of divide the traditional approach as well as the modern approach according to the challenges we're facing here. If you look at the traditional approach in optimization and decisions, information is generally assumed to be centralized. There's a single fusion center or an entity that controls all the information. We have moderate to large problem sizes. So we're thinking about decision problems with 100 or 1,000 variables. And then we have a single optimization control objective. So if you think about the resource allocation problems I was thinking about, generally the goal is design routing algorithms to minimize congestion, to minimize delay so that the packets arrive their destination in a reasonable amount of time. So we're thinking about designing algorithms, and we assume that the users and applications in our system abide by those rules. If you look at modern systems and applications, they pose new challenges. The first one, Tamer Hocam also talked about it, information is decentralized. So we're thinking about, here a small example is a sensor network. We have large systems, many sensors collecting decentralized data, connecting many agents worldwide with heterogeneous privately known preferences. So it's hard to imagine or actually impractical to design a system in which information is in a centralized entity. Problem sizes are huge, very large. So thanks to advances in technological online platforms, automated markets, we see basically data collected at a speed that has never been seen before, which leads to optimization decision problems that are very large scale, very high dimensional. And the other aspect is, I think smart grid is an example that we're picking today, but this happens in many systems. We no longer have systems that are controlled by a single administrative domain. These systems are interconnections of autonomous entities. So if you think about the smart grid again, this is a system that consists of decentralized competing generators. We have the transmission network that is regulated by ISOs, distribution networks controlled by utility companies. On top of it, on the smart grid aspect, we have, thanks to these smart devices, thermometers, etc., we also now have an active demand participation. Consumers are also, through direct or indirect load control programs, actively participating in this market. So this is really not really looking like an engineering system, but rather like a market in which we have multiple participants active strategic users and multiple objectives. There's another aspect that I would like to highlight, and this sort of brings this impact of network or this network element in these applications. Network structure is an important determinant of both how technological systems operate and how economic and social interactions take place. So Tamer Hocam showed some examples. If you look at the power grid as well as the transportation network, clearly, congestion in these systems is very much a function of how these links are interconnected to each other. So it's determined by the underlying network structure, which clearly affects the overall performance. And if you look at economic and financial systems, they look much more like networks rather than anonymous marketplaces, as economists assume, in which everyone interacts with everyone else. It's rather a network in which every entity interacts with a local neighborhood. So this is one example. It's the input-output linkages between 400-something industries, sectors in the U.S. economy. And here, basically, a link is present if a sector uses as input the output of another sector for its production. Think about automotive industry using the output of glass industry to produce cars. So this is clearly another network which determines how the aggregate production looks like in the U.S. economy. So this sort of broad challenges necessitates new optimization and control methods that are fast, scalable so that they are able to deal with these huge amounts of data, operate in a distributed manner whenever the information is decentralized, and finally recognize the role of human element in these systems, as well as its interaction with the network structure. So this is an emerging area that sort of is attracting attention more and more in the last decade or so. It's very much at the intersection of engineering, computer science, economics, OR, and other quantitative social sciences. And the key tools we see in analysis of these problems are optimization and control theory, of course. We're looking at dynamic decision problems, but also graph theory, stochastic network analysis, and as well as economic modeling, game theory, and incentive or mechanism design. And what I'll do in this talk, I don't have a lot of time, I'll rush, but I'll try to basically first discuss quickly the evolution of fast methods in optimization. Basically, I'll sort of, driven by this technological changes I mentioned, the evolution from sophisticated, very popular interior point methods to simple, computationally very cheap, gradient-based first-order methods. I'll talk about some of our recent work on designing fast and scalable gradient methods for incremental optimization for large-scale data processing, as well as quickly decentralized optimization over networks. I'll then discuss quickly about designing optimal control algorithms for rapid containment of contagion epidemics over networks. And very quickly touch upon at the end how game-theoretic models emerge in these problems and how they guide the design of incentives for control of these systems. So this is sort of, I was thinking when Tamer Hocam was talking about advances in our area, communication, control, information decisions, everything happening in this time window, 40s, 50s, I was actually going to make the point that the revolution has in fast methods in convex optimization happened in 80s, 90s. I think in optimization also, the cornerstone of simplex algorithm was in 47, DAN6, very much driven by the need for resource allocation problems in that time. But we see basically one of the other big leaps during the 80s when the interior point methods with provable polynomial time guarantees have been discovered. So what do I mean by polynomial time? In optimization, generally fast is synonymous with polynomial time, and that means basically that the runtime of the algorithm is polynomial in the problem's dimension. Think about it as n squared, as opposed to some naive algorithms performance, which is something like a 2 to the n. If you enumerate everything possible, that will be some exponential dependence. So for small n, this may not be as big of a difference to you. When n is 3, this is not really important, 2 to the 3 versus 3 to the 2. But think about n 100 to the 100 square versus 2 to the 100. And as n increases to the levels I'm going to talk about, millions, this is a huge difference. So polynomial time, the invention of polynomial time algorithms was a big improvement, considered a revolution. And I've actually included some news clips to highlight the excitement at the time. This was the first sort of provable polynomial time guarantee algorithm was invented by 28-year-old mathematician Karl Markov. Karl Markov was working at AT&T Bell Labs at the time, and his invention just created such excitement. And this is an article from New York Times. There's one from Time Magazine, 84. It talks about various industries very excited about this invention, ranging from American Airlines at the time trying to use this, interested in using this algorithm to schedule their 1,000 jets at the time, together with 800,000 passengers, 4,000 crews. Two investment companies interested in using this algorithm again to design their portfolios and so on. So various diverse set of industries. And I actually picked this quote from Ronald Graham, Director of Mathematical Sciences at Bell Labs. He calls this basically, breakthrough is one of the most abused words in science, but this is one situation where it's truly appropriate. So this was basically considered a huge leap and created a lot of excitement in the optimization community. 80s and 90s have seen probably the largest area of research in interior point methods. This was for linear programs. Think about optimization problems characterized by linear systems of equalities and inequalities. So people have worked to extend this, both the complexity theory as well as the algorithms, to a certain class of convex problems. There's the seminal book that talks about all that work by Nesterov and Nemirovsky, interior point polynomial algorithms and convex programming. So this is great. What it means theoretically is the running time is polynomial in the problem dimension as well as the number of accuracy digits. And what it says is moderate scale problems can be solved very fast to high accuracy. So what's the problem practically? The running time is dimension dependent. So the problem dimension n dictates the running time, and it grows non-linearly with the problem's dimension, something like n cubed if you're using a Newton type interior point method. And what does that mean? Let me pick an example to show you the implication. This is a PET imaging problem, so using PET data from PET scans, try to construct an image. And for reasonable resolutions, 64 by 64, it translates into a problem dimension for the imaging problem of 250,000. And if you increase the resolution to 128 by 128, and increases to 2 million. If you use the best IP method on this problem, the CPU time per iteration of the method is, in the first case, 2.5 hours, in the other one, 2 weeks. So for all practical purposes, it's not doable. So the point is, interior point algorithms are great for moderate-sized problems, but whenever you go into large-scale problems, they're pretty much useless here. And this is not a degenerate problem. We see here right now, thanks to developments in acquisition and storage technologies, we have amazing amount of data. The industry actually refers to this trend as big data, a very popular term both in industry and academic circles. A lot of money poured into it, all institutions opening data science centers left and right. Basically, the driving force behind this is data sets are often large, consisting of hundreds of millions, billions of data points. And data is often high dimensional because we can measure very rich characteristics of these data points. So this now motivated the optimization community to go back using these simple methods, gradient or so-called first-order methods. They are very simple, and the important piece or characteristic of these algorithms is that they have dimension-independent running times. So this n, which is very large, 10 to the 6 million, doesn't go or dictate the running times of these algorithms. And the implication of that is you can get perhaps not high accuracy, but good approximate solutions very fast. There's another sort of structure in these sort of large-scale problems. Objective function also takes the sum of a large number of component functions. So we're minimizing some f of x. This is a very simple problem. Objective function is f of x, and we generally can write this f of x as the sum of fi of x's component functions. And think about these fi of x's as loss functions or objective functions associated with data points, and m is our size of our data set. So you're essentially getting loss functions associated with each data point or block, and you're summing it over. Okay, so it has this because you have these data sets, data points, your problem also has this additive structure. And for big data applications, not only n, but also m is large. Okay, so we have basically this problem to deal with in this thinking about how to design optimization algorithms. So I was going to give you sort of an example to show why that additive form emerges, especially in machine learning applications, but I'm going to skip this. Basically, you can just think about it as we have some feature vectors, target outputs, and we have m of them. Each one of them, we want to build a model explaining the unknown input-output relation using all of these data points, and you can actually turn it into an additive cost problem. This emerges in regression problems and support vector machines, classification problems, and so on. So n is large, m is large, so gradient step will not be very reasonable either, because a full gradient step will involve summing all those individual gradients and going over this whole m. Think about m again in the order 10 to the 6th. So you have to touch all of these data points to take a single step, which is not feasible. So what this motivates is using incremental algorithms that can actually exploit this additive structure and process component functions one by one. So I'm not going to add the full gradient to make just one step. I'll just think about the first component gradient fi, take a step, and hope that by doing so, I will make reasonable progress in my algorithm. And this is also well suited for problems because we're, processing all of these component functions one at a time. These algorithms are also very well suited for problems where these FIs are distributed. I can first take F1, process, go to the other processor, take F2, process, and so on, as well as online applications, dynamic applications, where FIs are coming to me sequentially. I don't have access to all of them at one point in time. So what are incremental methods? I just tried to write it in a very simple form. So here's our problem. I'm going to update my decision vector. I'm going to take my current iterate xj, take a step, normalized by some step size, take only one of the component gradients, and move in that direction. So an important consideration in these methods is how do I choose which component gradient to move along? So I can do F1, F2, F3, F2, F1, F3. How do I choose this order? And one immediate order that one can think about is a deterministic order, simplest being a cyclic order. Just go through in a round-robin fashion in cycles, 1, 2, 3, 1, 2, 3, and that gives us this cyclic incremental gradient method. The other one, which is very popular, is random orders. Just pick your component functions randomly from the collection. And you can think about different randomizations. Again, a very popular one is the stochastic gradient descent, in which at every point in time, you pick the component to process independently and uniformly at random from the collection 1 to m. Okay? So you may have repetitions. You pick 2, and then again independent choice 1, another independent choice 1, and so on. And then the other randomization that sort of is popular is random reshuffling, which instead of at each iteration picking a component randomly, at each cycle it picks a random order and processes according to the random order. So deterministic order, random order, and at each iteration pick your component functions randomly. Okay? So this may have repetitions clearly because you're not choosing the orders. So let me talk about SGD. This is the one which picks the component functions randomly at each point in time. And that's the most widely used optimization method in the machine learning practice since 50s. Nowadays, it's extremely popular. If you go to any workshop that Google holds, basically this is sort of the most popular method they're talking about. I just wanted to highlight here how simple it is, yet how popular. And mostly popularity comes from, for them, for training, for deep learning, very deep learning, and training deep neural networks, because these are problems that are, again, very large dimensional and very large sizes. And it's the default method for data analysis in industry, ranging from training neural nets, deep neural nets, as well as recommendation systems, again, because of the fact that we're dealing with large-scale data here. And there's a large research going all the way back to stochastic approximation literature, but again picked up in computer science, machine learning communities. And the important thing, sort of, that I wanted to highlight from this for this method is that running time is not only independent of problem size n, but also this data set size m. So all these big things I was talking about, 10 to the 6, 10 to the 8, do not go into the runtime, determining what the runtime of the algorithm is. And random reshuffling, which is what I just mentioned, is this method that's also used a lot in practice. It's a different randomization. There's much empirical evidence showing it outperforms SGD, yet there's no analytical results. And there are some, this is one example from a classical paper of Boteux that shows in a classification problem with problem size 10 to the 6, data set size 10 to the 8, that SGD converges at a rate 1 over k, whereas this random reshuffle converges at rate 1 over k square. This is empirical, but there's no analysis. And this is sort of one of the long-standing open questions in the optimization literature. This is a quote from Bert Zekas. And analysis is hard because of dependencies of gradient errors across and in cycles. So this is one of a result from our recent work. Basically, our goal was to analyze random reshuffling, and the way we did this was we first analyzed the deterministic methods, provided the convergence rate guarantees. This is a deterministic method with any order that you can pick these component functions with. And we used that idea to be able to analyze random reshuffling. And let me just put on one slide the results for stochastic gradient descent, this popular method that everybody is talking about, versus random reshuffling. And what you can see is for stochastic gradient descent, we have a 1 over k rate convergence in function values, whereas the random reshuffling has this 1 over k square rate. And the convergence modes are also fairly different. What you can show for stochastic gradient descent is a convergence in distribution, whereas this is a much stronger concentration, convergence with probability 1. So this is a little bit technical. I don't want to go into the details, but I want to make the point that even though this is an area that's been studied for many, many years, there's still much to do and much to understand in the context of these algorithms, and that are very insightful. So I just wanted to put an example. This is sort of how the error behaves in the two algorithms. As you see, the random reshuffling, these are the histograms of the scaled approximation errors. You see that random reshuffling concentrates very quickly, whereas SGD has this quite a bit non-trivial variance in the error that's achieved in this method. So these algorithms can also be used, because these are sequential, for designing distributed algorithms over networks. I'm going to skip over this because I clearly don't have time to go over that. We can think about using these first-order methods, combine local computation together with local communication to design algorithms, and still show similar convergence rate guarantees, even though you're doing everything locally. Everybody is doing something based on their own information, communicating according to the network. We can still get similar convergence rate guarantees, iteration complexities in these methods. And we can use other ADMM type methods as well. So I want to say just a couple of things. How many minutes do I have? 2 minutes. So far what I talked about was how to do large-scale, how to design optimization algorithms when you have large-scale data. I also want to mention some ideas about how can one think about controlling dynamics over networks. And these dynamics generally are referred to as contagion or contagious processes over networks. These could represent many different interactions in many different applications. Tamer Hocam mentioned epidemics. This could be, you think about a social network of contacts, epidemic passing from one individual to the other because of contact. This could be security attacks. Think about computer viruses going from computer to computer because of malicious emails and so on. This could be financial risk, sort of defaults going from financial institutions, one of them to the other, because of, if you're not able to pay your debts, then, that triggers another cash problem in the next financial institution. So applications are diverse. And the sort of fundamental characteristics of these problems is that these interactions take place, again, with a local neighborhood, with your local contacts, and the overall network structure is the propagation medium for how these aggregate and form some aggregate effects. So to just highlight the importance of dynamic control with limited resources in this area, just these are a few examples. This is from 2014. Ebola drug could save a few lives, but whose? So we have limited number of vaccines. How do we think about allocating these vaccines to individuals? Another one is from supply chain. Supply chain disruption, major threat to business. This article highlights the importance of dynamic interventions to minimize the impact of a disruption. And similarly, in the context of financial systems, if you want to take intervention, how do you do that? And if you look at the literature, this is a literature mostly in computer science and OR as well, they focus on static strategies for control of such processes. So ex-ante targeting of some central nodes in the system so that those nodes act as a sort of buffer to contain this epidemic. So static interventions. But as I've been trying to highlight, in many cases we have access, dynamic access to the evolution of this contagion. Information about where it is, how it's spreading. So if we have such dynamic information, how do we think about allocating these limited resources, vaccines, at each point in time? And that's sort of, I think, an important question and what we have tackled in our recent work. We considered a stochastic contagion model, an epidemic model that's studied in epidemiology, and asked the question, how can we think about rapidly curing agents under a fixed resource budget? And this is a stochastic dynamic decision problem over a network, which is a very combinatorial structure. Discrete sets of nodes. So it has, you know, mathematically all kinds of challenges. We designed a policy which we call cure policy based on a novel concept related to a graph, which is cut width. So I'm not going to define, I don't have time to define it. It's just all I want to say is it's a concept which is efficiently approximable. So you can actually develop efficient algorithms to compute what the cut width of a graph is. And we provided a sharp characterization of when it is possible or when an epidemic can be effectively contained. If your curing resources is greater than this cut width of the graph, then cure policy is optimal in the sense it rapidly cures or contains this contagion. And when it's not, then no matter what you do, you cannot contain it. So you cannot effectively control this contagion. So basically, this is an example of a work in network science. You have these very complicated networks. You want to design policies to control behavior or operations over these networks. In order to make such decisions, you try to come up with some relevant macro property of the network that will dictate what you need to do in your policy. So you can't really model the entire network. It's too huge. What's the relevant macro property? It turns out in the context of optimal dynamic curing, it's the cut width of the graph. And we have basically first some simulations to show its effectiveness. This is a degree-based policy, dynamic degree-based policy. And this is our cure policy. And then this is an actually empirical exercise using data from Center for Disease Control. So this is in the state of Massachusetts, H1N1 virus numbers. These are the number of infected people, number of vaccines administered according to the policy that CDC is using. And of course, this is the only data that you have available here. You don't know the network structure. So what we do is here first assume some parametric form and fit it. We assume some scale-free graph for the contact network that dictates this epidemic. It seems to be a fairly good fit. And when we simulate our proposed policy, we see that the number of infected people actually decreases significantly. So I'll actually stop there. I was going to give two examples about game-theoretic models. Maybe I take 1 minute. Thank you. I haven't talked about game-theoretic models here. I talked about large-scale data. I talked about large-scale networks. Another important component of these problems is that individuals forming these networks are strategic. And in that case, game-theoretic models are used to describe the behavior of these strategic agents so that we understand when we have an intervention or a policy, how this behavior changes. So I just want to give you two examples where such models are relevant. One is, of course, very relevant context is traffic networks, where congestion is a pain in all of our lives. And it seems like the new horizon, at least for me as a commuting mom, is the GPS-based apps, Waze. So Waze gives you information about what routes to choose in the congested times. And we basically asked the question in our recent work, does Waze necessarily lead to reduced travel time for all agents? So providing more information, does that reduce your travel time? And the naive answer is, of course, the information is great. But we actually show here that because of all these game-theoretic interactions, the answer may be no. And we try to answer what network structures actually lead to information helping us and which of those not. And in the cases where it helps, what is the best information that can be provided to the travelers so that either their travel time or the overall traffic time congestion can be reduced? And similarly, another context where game-theoretic models arise is in this sort of very popular question of systemic risk in economic and financial networks. And this is mainly driven by the recent financial crisis. Systemic risk refers to the question that when some of the individual units in the network are hit with a shock, that shock propagates to the rest of the network, creating domino effects, cascaded failures, and potentially an ultimate meltdown. So the question again here is, what kind of connectivity architectures in the financial system amplify these effects, and which of them contain them? And in the case where you can amplify or contain, what kind of intervention schemes you can design. And this also is another example where you need game-theoretic models to understand how financial institutions behave, how they are interacting with each other, and so on. So with that, let me conclude. This is, I think, a very new and fertile research area. The thing I like is it's very interdisciplinary. It uses tools from many disciplines. It uses ideas from many different disciplines. And I also want to point out that this is the focus of the new institute at MIT, which was launched last year. This is the Institute for Data, Systems, and Society. This is an institute that sits within 5 schools at MIT. And the mission statement is exactly what I've been talking about: addressing complex societal problems with tools of information decision systems, social sciences, and statistics and data science. So with that.
Thank you, Asu.